An intelligent prosthetic arm, that is all about Project REACH. Synapse is a student club specialized in biotechnology. Synapse is based at the University of École of Technologie Supérieure. We are 25 student engineers in biosphere working on Project Synapse. Right now, we are working on 3 projects, and one of them is Project REACH. The goal of Project REACH is to offer a better quality of life to the amputee. A lot of prosthetics already exist on the market, but there's still a lot to improve on them. Usually, they're expensive, heavy, limited in that they can do. With that in mind, we have decided to create a robotic prosthetic hand controlled by Myo armband. Throughout this year, different milestones have been achieved on realizing on the software and the hardware.
To come up with a good prosthetic hand, we really needed to dig into what makes a great prosthetic hand. The first criteria that came up to our mind was that we wanted it to be strong, fast, and precise. But we also wanted it to be simple, lightweight, and power efficient. So we came up with this first prototype. All fingers were powered individually by microlinear actuator. We chose these actuators because they are small, lightweight, precise, strong, and fast. Also, the fact that they can hold their position when closed helps a lot on the power efficiency of the prosthetic. The thumb would have been a soft robotic tentacle actuated by 2-step motors. It would have allowed for multiple position of the thumb so the user could have different grips. But as we started building the hand, we noticed that our concept had multiple flaws. It was too heavy and too stiff. So we stumbled upon this open source concept called FlexiHand. We really liked the flexible Ninja Flex joints of the hand because it was a solution that could solve the issues with the stiffness of our previous hand. We ended up merging these 2 concepts to create our final prototype. Now composed of 4 linear actuators, 1 for the thumb, 1 for the index, 1 for the middle finger, and 1 for the ring and pinky. This last prototype was simpler, lighter, and way less fragile because of its flexibility.
Our goal is to make a fully integrated arm in which we'll be removing our dependency to the Myo and also finishing our printed circuit board. It will be able to fit inside with a battery on the forearm of our prosthetic arm. We're currently building a basis on which we can build upon. As of right now, we have fully integrated a classifying algorithm that can process EMG signal in real time.
Here is how this works. The Myo armband is directly connected to our microcontroller via a Bluetooth connection. It is placed with the limitations of our transradial amputee in mind. This position gives us access to 5 of the major muscles that are found in the forearm. The flexor digitorum profundus, responsible for forming a fist with our fingers, the extensor digitorum, responsible for extending our fingers, the flexor carpi ulnaris, partly responsible for wrist abduction, the flexor carpi radialis and palmaris longus, responsible for wrist flexion. But of course, these are not the only muscles in the forearm that are forming these poses. We believe that monitoring one muscle isn't enough, since it's a combination of multiple that form movement in our bodies. What we're trying to do with a learning algorithm is to model muscle synergies of distinct movement. With a total 700 repetitions, we built a dataset of just under 12,000 data points that were used to calculate the best threshold possible to classify 5 different states. We did not need to utilize a transformer on the dataset, since each movement is sufficiently different and that the muscles are far enough apart. Thus, the algorithm can linearly distinguish between them. At first, we used to process EMG signals through a linear support vector machine, linear SVM for short, on a computer then sent it out via Bluetooth to the hand, but this causes delays of over 2 seconds. The human body has a delay of around 300 milliseconds from the moment it sends a signal through the nervous system until there's a physical reaction. Because of this, we gave ourselves a more realistic goal of 400 milliseconds until there's a reaction. In order to reach this goal, we needed to integrate the classifier directly into the microcontroller's firmware. We accomplished this by transposing the same logic from the Python code to the C language, by simply extracting the coefficients and constants generated by the linear SVM. Here's a brief description on how the pipeline on the prosthetic functions. First, we accumulate data. Our process waits until we've received 50 packets from the armband. It usually takes about 250 milliseconds. Then we calculate the root mean square for each channel. The RMS equivalent will form a single vector of size 8, one value for each EMG sensor, then passes that vector through a standard scaler determined while analyzing the mean and standard deviation of the dataset. Finally, we perform a simple dot product for the final vector and coefficient, and we will obtain an either negative or positive value, where a positive value means a pose was detected. Since our algorithm is multi-class, we have multiple planes to test, and if multiple positive values return, then we output an other class. Simply means we do nothing. The largest problem we encountered was our ambition. It took us many months to finally decide to eliminate temporality from our architecture. The original idea was to feed data almost untouched into a recursive neural network in order to recreate the movement by correlating a chain of state changes. For example, from the rest to the opening hand to preemption to a closing hand. This would form a hand graph. But as we learned eventually, that would take in the millions of experiments to train a neural network. And we're not even talking about the problem that would occur when trying to implement a neural network into a simple microprocessor. But one of us was actually able to recycle this work and transform it into another version.
So this year, our team had to do a little bit of restructuring in terms of the different projects we have going on. And what that means is we had to take a step back and think of the different applications we want to apply our tech stack to. And what we realized is we don't necessarily want to limit ourselves to just biomed applications. We want to be able to do consumer electronics and ergonomics. Now, the first step to being able to target that kind of market is to build a hand movement classification system that's a lot more precise than what we have going on for the prosthesis system. This means, well, if you look at the prosthesis system, we're doing detections on movements of a much larger scale. Now we want to bring that scale down to little movements of the fingers. Now what that means is that we had to rethink our whole classification approach, and we had to rework our signal processing and extraction pipeline. Now let's take a closer look at our system in action. All the user has to do is wear the Mayo armband and launch the program on a laptop. Our system will then pull the raw EMG signals from the band and start recognizing the poses held by the user. As of now, the system can recognize 5 different hand poses, which are a resting pose, index flexion, middle finger flexion, ring finger flexion, and pinky flexion. You can notice that there is a bit of delay between the movement and the system response, and that's because we want to reduce the uncertainty of the classifications. Basically, we don't want a jittery response. You can also notice that we use this really cool rendering of the human hand to display the poses. This comes from a project called LibHand. If you guys are into that kind of stuff, you should definitely check it out. The project is all open source and it's well maintained. For more details, take a look at our documentation, which is linked below. Now back to the project. In terms of future development, our next goal is to integrate the recognition of contraction movements, and ultimately we want to be able to modelize the whole human hand and recognize movements in real time. Now, On the technical side, the system works a lot like the one used on the prosthesis, but our team had to make some key changes. Since the differences between the poses are subtle, we had to figure out a way to extract more information from the signals. This ultimately means performing more computation while also keeping a real-time performance. And for us, this was the point where the possibility of using a microcontroller went out the window, because we needed more processing power. This process took us a while because there's a lot of different possibilities to explore, and to figure out the best ones, well, it's mostly trial and error. So in the end, this is the classification pipeline we came up with. At the first layer, we use MAV instead of RMS to average out the signal. This allows us to represent the input EMG signals with 32 points instead of 1,600. Now, still at the first layer, we also use discrete wavelet transform, or DWT, to extract frequency information from the signals. The extracted features are then concatenated and passed to the second layer. At the second layer, we use PCA, or primary component analysis, to reduce the dimensionality of the data we extracted. It allows us to bring the data from around 60 dimensions to around 10. Then at the final layer, we normalize the data so it can be classified by an SVM. Here's a representation of the movement types plotted against the two first components out of the PCA layer. We can see that at this point the data is almost perfectly linearly separable. Because of this, we decided to go for a linear SVM instead of a polynomial kernel SVM at the classification layer. Now this concludes the tour of this project, but if you're still curious and want more information, well, check out our GitHub.
So with everything we have presented, this is the project REACH. For the next year, we have many milestones that we want to achieve. One of the milestones is to have force detection on each finger. Another milestone is to build ourselves our own EMG since Myo armband is no longer supported. We still have a lot to do, but with us, reaching higher will now be possible.